at high school, we had a very good physics teacher, and the main bit of equipment we had was an oscilloscope where you could see electrical signals. Physics and mathematics, I think, sort of underpins my interest in science and has helped me through my career. It ultimately led to the notion that matter could be regarded as either particulate-like or wave-like, and the development of quantum mechanics. These solar cells that were incredibly expensive could be made cheaply if only a bit of research was done on them. I had 6 PhD students from China during the 1980s and 90s, and all of them ended up either founding a company in China that became one of the major manufacturers, or acting as a senior technical person in the companies that someone else founded. We can supply 100 times our present energy use from solar and wind, 100 times what the world's presently using fossil fuels mainly.
Each one of us feels the impact of climate change almost every day. Last year, the year of 2023, was the hottest year in the recorded world history. And so was the year before that. And by all indications, 2024 would be yet another record. We also see a lot of other implications on the climate change, such as increasingly powerful cyclones, heavy unseasonal rains, landslides, significantly diminishing biodiversity. And we see all of that every day across the world. This climate change, we all know, is because of the burning of fossil fuels and the significant generation of CO2. And it is now agreed all over the world that what we need to do is to replace fossil fuels with renewable energy. And we are very fortunate that now there is good news, at the horizon. In the last year, the renewable capacity in the world went up by 50%. And it has been going up like this for the last 20 years. As the scale of the renewable energy has gone up, the costs have plummeted. A lot of the renewable energy, last year's renewable energy addition, 75% of that came from solar photovoltaic. In the last 50 years, the cost of solar modules or solar cells have come down by 99.8%. Can you believe that? 99.8% in the last 50 years. In the last 5 years, every year, the costs have dropped by 15%. Compounded over the last 5 years, and you can see almost a 90% drop. Today, it is cheaper to have electricity from solar than to have from natural gas or from coal. The good thing is that the amount of sunlight that we get within an hour, the light that the sun showers on Earth within an hour is more than the energy that we consume, the whole of humanity consumes in a year. So just imagine what kind of potential solar photovoltaic can have in creating huge amounts of renewable energy. So as a matter of fact, solar photovoltaic might provide really a beacon of hope or a tremendous blessing for a sustainable future of the world. 90% of the installed solar photovoltaic cells come from the technology delivered by our guest today. I'm indeed thankful to you, Dr. Green, for being with us. And it's such a pleasure and honor to have him with us here in person today. What we would like to do is to talk about him, talk about what he has done over the years, and look at what does he see as time to come. So let me first introduce Dr. Martin Green to you. He is a Scientia professor in the University of New South Wales in Sydney, Australia. He is also the founding director of the Australian Centre of Advanced Photovoltaic Studies. This center coordinates activities of multiple universities and research groups across Australia. His group's contributions to PV are well known and include holding the record of silicon cell efficiency in 30 of the last 40 years. 30 of the last 40 years. The PRC silicon cells that he invented and his team developed way back in 1983 today account for over 90% of the solar photovoltaic capacity across the world. Dr. Green has won many accolades, many awards. The Right Livelihood Award, also known as the Alternative Nobel Prize, the Solar Award, the Solar Einstein Award, Global Energy Prize, that was in 2018, the Japan Prize in 2021, Millennium Technology Prize in 2022, and the Queen Elizabeth Prize for Engineering in 2023. He has authored or co-authored over 15 books on photovoltaics. A truly extraordinary personality. So thank you again, Dr. Green, for being with us. As you know, the audience for our program are the young, aspiring, budding scientists and engineers. And what we would like to do is to actually take them through your background, your experiences, because I believe that it will motivate quite a few of them to pursue careers in different branches of science. Now, in the the very exciting conversation, the fascinating conversation that we had the other day, you mentioned that you were the first in your family to go to college. Now, we have many young Indians from the generation which is the first generation to go to colleges. And so what we would like to ask you is that what was it in your school or in your family that this first generation college graduate became such an outstanding scientist and engineer? What were the abiding influences? What drove you to the direction in which you went?
Yes, I had a very exciting career, but I guess what started it was always at school, mathematics and the sciences were probably the subjects that I performed best in. So that sort of guided my career in that direction. And I guess like many people at high school, trying to decide what subjects I wanted to study at university, was a big decision. But at high school, we had a very good physics teacher, and the main bit of equipment we had was an oscilloscope where you could see electrical signals. So a lot of the experiments we did were based on electrical circuits and so on. So that got me interested in that side of physics. And so I decided to do electrical engineering when I went to university, and that sort of shaped the rest of my career. There were some exciting things happening in electrical engineering in that era, and one of them was the development of the microelectronics industry. So transistors had been developed in the 1950s, and then, towards the end of the 50s, people started looking at compounding transistors together into a circuit. And by the late 60s, when I was doing my undergraduate study, people were starting to make integrated circuits. So, first of all, there was 4 transistors and then 10. That was about the stage I got interested. And so I got very interested in microelectronics in my final years at university, which sort of drove me into the semiconductor electronics field where I've ended up.
But I read that you did your BSc in mathematics and molecular biology. From there to electrical engineering to com science, PhD in com science. So,
I went from electrical engineering to engineering physics. So that was the only diversion in my career. So I got more interested in the physics side, and did my PhD in engineering physics. And by then I'd got interested in solar, and that was the focus of my career when I started work as a young academic.
Now, this is very interesting because we come across a lot of people who had done exceedingly well, whose basic education is in physics. And I think that a deep insight in physics probably helps you understand the world much, much better. Could we say that?
Yeah, I guess so. Yeah, so there's a diverse range of topics within physics, and yeah, so I guess it broadens your outlook on how the world works and so on. So that physics and mathematics, I think, sort of underpins my interest in science and has helped me through my career. In in the solar fields, you've had to branch off out of areas that you're familiar with into other areas you're less familiar with, and I always find that interesting part of my research.
Yes. No, so for the benefit of our audience, can you give a little bit of insight into the photovoltaic technology that you mentioned you have been working at for the last 50 years?
Yes.
So how the field that changed, and how do you see the movements in this field over the years?
Yeah, so it probably all started with Albert Einstein, the photovoltaic area, because he, so light had been shown to be waves in the made of wave-like motions of particles in the 19th century, but he turned it back to Newton's original idea that light was made of particles. So Newton thought because sunlight had very sharp shadows, that it couldn't be waves because they would sort of wrap around objects and blur out shadows, the edges shadow. But Einstein boldly postulated that some of the effects in physics that were poorly understood could be explained if you regarded light as being particulate-like. And of course that was very important because it ultimately led to the notion that matter could be regarded as either particulate-like or wave-like, and the development of quantum mechanics, which have been important to the development of modern science. But Einstein's experiments were initially explaining when light hits a metal, you can get electrons that get shot out of the metal when the light is absorbed. And he explained that as light acting as a particle and imparting energy of a known amount to the electrons in the metal. And the photovoltaic effect is, very similar to that, in that the light excites an electron in the material to a higher energy, not high enough to shoot it out of the material, but keep it in there and do something useful. I guess the first solar cell was made in 1839 by a Frenchman, Becquerel, although it was based on liquids and probably you wouldn't really call a solar cell by present standings. But by the late 1800s, people had made devices that could convert light into electricity, although they weren't terribly efficient. And just the physics behind it were not understood at all until Einstein postulated the particulate nature of light. So, there was rudimentary devices available in the early 20th century, but the real development happened from 1940 onwards, and the first efficient cells were made in the 1950s. And an industry developed supplying solar cells for spacecraft.
Yes.
Because they were sort of ideal for that, not requiring anything but the sun to provide the electricity.
Yes.
So that was what started the industry, but they were incredibly expensive. For spacecraft that wasn't too important because the whole space mission was incredibly expensive, so the cells were only a small fraction of the total cost. But that industry sort of underpinned the development of the industry that has evolved for using solar cells here on Earth, which really started in the 1970s with the oil embargoes that came into being in the early 1970s. That's stimulated interest in other ways of generating electricity, and nuclear was the big favorite. But the people involved in the solar industry managed to convince the powers that be that these solar cells that were incredibly expensive could be made cheaply if only a bit of research was done on them, and that sort of kick-started the interest in making cheap cells for use here on Earth. And it's taken sort of 50 years for that to eventuate, but now the solar cells provide the cheapest way of generating electricity. So the initial I guess, enthusiasm of the space cell people in promoting solar for terrestrial use, has paid off.
Yes. So could you tell us a bit about the technological changes that have brought us to this? The other day you talked about the tunnel part, and then you talked about the PRC. If you could explain a bit of that.
Yeah, so the solar cells are made from a material known as a semiconductor.
Yes.
And, the three types of materials: metals, insulators, and semiconductors. And the semiconductor is like a in-between material between the metal and the insulator. But what happens is it has a range of energies that electrons can't occupy within a material. So the photon of light excites the electron from a lower energy that it can, most of them are occupying, up to this higher energy state where there's a gap between that and the original state. And then the solar cell's designed to make that electron move off in a desired direction. And then if you put contacts between the front and the back of the cell, you can get the electron flowing around the circuit that's formed. And any electrical load that's in that circuit will have the electron flowing through it, and the electron could generate energy in that load. So it's a very simple process physically. In terms of what happened, it's just electrons moving from the semiconductor through the load, generating power. But the physics behind it, is one of the major developments in the 20th century, the development of quantum mechanics and understanding of semiconductors and so on. And it was one of the big developments of the 20th century. So the physics are, quite complicated, which is sort of what got me interested in the field, But the actual process is very simple, which means the cell's very reliable because there's no moving parts or anything that can wear out in principle.
Yeah. So what is PRC? And what does it do differently than the old cells?
Yeah, so to get the electrons moving off in one direction, what's built into the cell is what's called a positive-negative or PN junction. And the PN junction is the basic building block of microelectronics because it has an asymmetrical property in that it will let electrons flow in one direction but not the opposite, which is exactly what you need for a solar cell to get them going in the same direction. So it turns out that the current generated by a solar cell just depends upon the number of photons in the sunlight. So all these particles that Einstein postulated are now known as photons. So the number of photons in the sunlight determine how many electrons are excited and ideally can flow through the load. But the voltage depends upon the size of that gap that I mentioned, the what's called the band gap, the gap in energy, so that electrons can't occupy in the semiconductor material. So it's some fraction of that. And that fraction depends on the design of the cell. And so when I started my research in the 1970s, there'd be a lot of progress in developing the current output of the cell, but it was this voltage output that was sort of, I guess, there was scope for improving it. It was lower than some of the theoretical calculations were suggesting. And so that's the area that we were focusing on, ways of improving that voltage output. And it depends upon the quality of the cell design. So that's where we focused on, was improving the cell design quality and then increasing the voltage output. And the power output that you can get from the cell is the product of the current and voltage. So, every improvement in the voltage you could make transferred to the power output and the conversion efficiency of the cell. So for my PhD thesis, I was given the job of looking at structures that involved tunneling through insulators. So I mentioned before that metal insulators and semiconductors are the three important states of matter. That an important semiconductor device uses the combination of the three a metal insulator semiconductor structure, was the basic building block of microelectronics through, the recent decades. But the insulator is made very thick in those structures and no current flows through it. But my supervisor was interested in what happens when you make the insulator very thin, and quantum mechanics tells you that when that happens, electrons can flow through this material, or that the insulating properties would normally prevent that from occurring. So my job was to look at that structure and understand how it operated, and because I had an engineering background, look at some applications in microelectronics that the structure might have. And one of the applications was in solar cells, which turned out very useful because it had some advantages over the...
Yes.
This structure could be used to give the directional motion to electrons that are required for the photovoltaic effect, but it had some advantages over the traditional positive-negative or PN junction, and that requires that you introduce impurities into the semiconductor to get that junction formed. Whereas with this MIS structure, you could just build the rectifying part of the circuit on the surface of the semiconductor.
I see.
And that proved to be important in improving the voltage output of the cells. So our early contributions were just in improving the voltage output of the cells. And fortunately, that was a focus of international research effort at the time.
Yeah.
And it's very easy to measure experimentally and to make a device that can demonstrate the potential voltage output from a completed cell. So it suited the low level of technological capabilities that we had when my lab started. So it was we were very fortunate in that there was such international interest on this particular parameter, because it established our international reputation even before we had much infrastructure or facilities to support our research effort.
So you mentioned about the journey in the increase of solar cell efficiency, 17% to 26%. I read recently a note from you which talks about the work done at Fraunhofer and in China, which talks about almost like 33% or so. So in the journey that you have seen, were there like unique aha moments where you saw that, hey, this will make a difference? Or it was like continuous, hard, dogged, persistent work which showed small improvement at every stage? What was it?
Yeah, it was a combination of both. So we started with these tunneling structures where the insulating layer is very thin, and that got us high voltages. Then we converted that to improved cell efficiency. So initially we used the tunneling approach for the cell structure, and that's now been commercialized as what's called TOPCon, TOPCON technology. But then we found when we heated these devices to try and tune their performance we could heat them to higher temperatures than we thought they could stand. And what we thought was happening was the metal was penetrating through this insulating layer in small areas, and was reducing the resistance associated with the current flow through that. So he said, well, we'll try just very small area contacts to get the same effect as this sort of filament penetration of the insulating layer. And that gave rise to the PERC structure, which basically depended on having small area contacts to get the desired directionality into the properties of the contact. And so our first world record was with the tunneling structures, but all the rest of the world records we set in improving silicon cell performance, and I think there was 13 or 14 of them successively, were based on the small area contact. So we had a conceptual jump from the tunneling structures to the small area structures, and then it was ongoing improvement and increasing sophistication in the techniques we were applying to these small area contacts as we delved deeper into their physical limitations and so on. Yeah. So as I said, the 13 or 14 steps we had. So we incrementally improved the world record each time. And the whole developmental process took 20 or 30 years. So it didn't all happen overnight. So, it was hard work, I guess.
Yeah.
But, the good thing about it was each little step, it created a real level of excitement within the laboratory and provided a great motivator for the researchers involved. So, they occurred, every year or so. So it was within the period of the research thesis of most students. So they got to experience the exhilaration of being involved in setting a new world record.
Yeah.
So that was a great motivator for the researchers in the lab, and working hard to understand how we could improve the previous record and trying approaches that were suggested for how we could do it. And most of them turned out to be dead ends. But then finally you hit upon the approach that does bear fruit, and you get the jump in the efficiency record. The good thing about the solar field from our point of view was these records were independently certified. So every time we had a cell we thought was setting a world record, I'd package it up very carefully and we'd ship it overseas to one of the international test centers to have it measured, and they would certify, yes, you've set another world record. So there was no sort of dispute about who held the record for silicon cell efficiency. And we held it for 30 of the last 40 years, without interruption, except for one little period where one group got ahead of us and we made us work harder to get our record back.
Yeah. Must have been a very exciting journey.
Yeah, no, it was. And, it was very motivating for those involved, trying to understand how to get the next jump in efficiency. So when we started, the best record by present standards was about 16.5% energy conversion efficiency. So about 1/6 of the energy in the sunlight was converted to electricity. And I'd done a study, in 1983, so some 40 years ago, that had shown that, you should be able to get to 25% efficiency. So that became, the target of our laboratory. And we eventually got there, but it took, 25 years from that initial calculation to actually demonstrate, and a lot of hard work in the year.
I can imagine that. So I was seeing the other day a video of a physicist, a scientist from the UK, talking about quantum biology.
Mm-hmm.
And so this was on photosynthesis.
Mm-hmm.
And she talked about the efficiency of 90% of photosynthetic processes, which include the electronic as well as vibration effects. Of course, photosynthesis had something like 3.6 billion years to improve.
Yes.
And the humanity has worked for probably in 50 years.
Yes.
So where do you see, how far you think we can push the envelope on solar cell efficiency?
Yeah.
And what would be, will they always be silicon? Of course, now there is talk about perovskite. Would they at any point in time be organic, live? Where do you see this whole movement going?
Yes. Like I think, if you look at the efficiency of plants and so on, they're not terribly efficient. So I'm not sure how this 90% figure was calculated. But
no. So what they said was the actual conversion was 90%. But if you look at the transfer from every node to the next node, there is a drop in that. And therefore the plants need to be highly efficient in the actual, the level conversion.
Yeah. So, like a solar cell is probably 90% efficient if you count the heat that's generated by the sunlight when it's absorbed. So it depends about what you mean by efficiency.
Yeah.
So if you count the heat that's dissipated in a solar cell, you've probably got 90% efficiency there. And some companies are interested in that combination of electricity and heat generated by a solar cell. But the limiting efficiency of a solar cell here on Earth is about 68%.
Well, 68% is
yes.
Awesome.
So that's a fundamental limit based on the physics of the processes involved. In space, it's somewhat higher because you've got a lower temperature that you can operate the cells at in space in principle.
Yeah. and no human-made pollution up there.
Okay. Yes, the sunlight is stronger up there too because it gets beaten about when it passes through our atmosphere. So we hold the world record now for converting sunlight to electricity at 40.6%.
Oh, is that so?
Yeah, whereas commercial panels now, the highest efficiency commercial panel is 24 to 25% efficiency. So we've still got a potential to getting, up over 40% commercial, which is, what I'd like to see, because the more efficient you can make the cell, the cheaper it's going to be to use.
Yes. So, the work that you have been doing has a phenomenal impact on humanity as a whole. And I think this is the result of the work of the head as well as the heart. How much have you been driven by this desire to change the world? And since when did you see the possibility of making such a significant impact? I mean, I would imagine that this is probably the most significant impact of science, especially in the current conditions of, the pollution that we have created or the CO2 that we have created. So what has driven you?
Yeah, I guess it was from, probably the 1990s that we were leading the world in the silicon cell development, and we could see that the potential of this to provide, energy, non-polluting energy rather than fossil fuels, in that era. So I talked about a race against time, because you could see, countries like China and India were going to be big users of energy down the track.
Yes.
And I could see that it would be better if they could generate that energy from, clean, renewable resources rather than from fossil fuels.
Yes.
So we were racing to get the technology to the state of development that industry could use it. So, we licensed technology in industry in 1987, I think it was, and some of our technology was put into pilot production here in India. We also, put efforts into getting technology into China, and some of my students proved very effective in doing that at the turn of the century. And, that's one of the reasons we have cheap solar cells now.
Yes.
My students in China were able to produce them much more cheaply than in, the countries that were the leading manufacturers before then, which were mainly the countries that were leading in microelectronics and had a different mindset about costs than the industry has now.
Yes. So you mentioned last time when we spoke that at the University of Utah in the US, you had like 1,000 Chinese students, and a lot of them then went back to China and made the impact.
Yeah, now this is at the University of New South Wales in Australia.
So you talked about Deng Xiaoping. That was in the University of New South Wales.
Yes. So that actually contributed greatly to the development of the industry in China. One of my PhD students had this interest in getting into solar cell manufacturing. He'd been working for one of our research companies, but he wanted to actually get into manufacturing, and our research wasn't sufficiently progressed to allow that to occur with the technology we're working on. So he set up the first commercial manufacturing line in China in 2002. And, that was a lot more difficult than it seems, because China had none of the infrastructure at all required.
Yes.
And, things like the glass or the solar panels he imported into China from Sydney, which is not the direction a lot of exporting and importing happens these days.
Yes.
So he had to build up the whole supply chain in China. But because of the other thing in our laboratory, operating from Australia, we didn't have the same type of budget that we were competing against in the US and Europe had.
Yes.
So we had to do things on a shoestring, and I built up a team of people that could locate second-hand equipment, mainly in the US, and we'd bring it back to Australia, and often we had to change we always had to change the power levels and sometimes the frequency that the equipment operated at to get it working in Australia. But we had this team of technicians who had the competence to do that. So that proved very important when my PhD student went to China. The first production line was set up in a shoestring in China, using the expertise so some of the people from our team joined my PhD student in establishing the first production, and they set up the production line on a shoestring there. So that was one advantage and that my student had over the international market, and then like labor and electricity and so on were cheaper in China, so they were able to compete with European manufacturers, which were the main competition in that era.
Yes.
So and I had 6 PhD students from China during the 1980s and 90s, and all of them ended up either founding a company in China that became one of the major manufacturers, or acting as a senior technical person in the companies that someone else founded. So 3 of the first 4 companies manufacturing in China were actually founded by my students. So
must be such a proud feeling for the teacher in you.
Yes, I'm very proud of that, and it was very important for the industry too, because I guess my student who first went to Australia not only set up the first production line, but he managed to get financing from US investors by listing on the US exchanges, because Chinese stocks were very popular, on US exchanges in the early 2000s. And these other students of mine were able to benefit from the same fundamental mechanism. So there were billions of dollars pumped into the Chinese manufacturing industry by US investors, from 2005 until the global financial crisis around 2008. And that also huge capital injection into the manufacturing industry in China, where they were able to fully use the money that was being spent, really was what kickstarted the modern industry.
I read somewhere that the investment, the new capacity created in China in 2023 was equal to the capacity created in whole world in 2022. The kind of rate at which they are growing it.
Yes, it's really quite amazing. And so the main the problem at the moment is getting it all out into the field. So what's really needed now is, I think, more ambition on the part of governments to fulfill their commitments to reducing greenhouse gas emissions, because the product is there and it's available cheaply. So we just need to keep the industry growing rapidly, and that will see the displacement of fossil fuels more rapidly.
I read somewhere that as the temperature of the world increases, the efficiency of the solar cells goes down. Do you consider that to be a problem?
No, it's not. It's not a big problem in that we're talking about like we're 1.5 degree temperature rise now, and that would reduce the output of a solar cell in relative terms by 0.4%. It'd be better not to reduce it by that amount, but it's not significant in the whole scheme of things. And the rate of efficiency improvement of the cells is improving at a much faster rate than that sort of loss that we've seen due to that 1.5 degree temperature rise.
So what do you see as the cost trajectory of the solar cells as time goes by? Because in India, now we have solar power available at 2 rupees. 2 rupees, and a rupee, there are 80 rupees to $1.
Yes.
So we are talking about 1/40th of $1.
Yes.
So what do you see the trajectory of these costs going forward?
So I guess that's been the bit of the industry that has exceeded expectations. It's just the rate.
Phenomenally.
The rate of cost reduction. So it's clear that the costs are going to go down further. And, already, according to the International Energy Agency, we're seeing some of the cheapest electricity in history from the solar cells now. And, that 2 rupees is probably, accounts for that in India. But, the cost is still coming down. So some people talk about that insanely cheap electricity further down the track.
Oh.
So I've tried to project the cost trajectory in the past, but I've always been too conservative. So you say, well, it can't go any lower cost than that, but it does. And I think that is going to happen. So some people, we can supply, 100 times our present energy use from solar and wind, 100 times what the world's presently using fossil fuels mainly. So there's plenty of availability of energy to supply from solar energy. So some people are talking about the third energy revolution, the first being the agricultural and the second the industrial, and third one being an energy revolution driven by this low-cost solar and readily available energy from solar. So so that might be the type of scenario that eventuates one where energy is cheaper than it ever has been before by a long way.
Yes.
And there's all the kinds of things that you might be able to do with that cheap energy.
So do you think that this reduction in the cost will happen by increase in the efficiency? I mean, you talked about the potential of 68% at some go,
yes,
and maybe commercial at 40% efficiency level. So you think, is that going to be the main driver of cost reduction?
It's been a big driver historically. So there's been some studies that have concluded it has been the largest driver of some periods of development. But the scale of the industry, like every year, the industry looks to equipment that has a higher throughput, and the factories are becoming bigger and more automated and so on. So all those economies of scale have been the other important factor, I think, and the strong competition within the industry. So we're in a period of over capacity now. So there's more solar cells available than the market can absorb, and that is a big downward driver on price.
Yes.
So the companies that will, so what will happen will, because of that oversupply, is some companies will disappear.
Yes.
But the ones that survive will be those that can reduce the cost of making the cells below the prices that they're able to sell them for at the present. So, so that's an enormous accelerator of cost reduction has been the competition within the industry. So we've sort of been free market forces at work there that have really brought the costs down.
Yeah. So when do you see we may have a situation where the world doesn't use any dirty energy at all? So what combination of wind, solar, and energy storage you think will take us to the nirvana? That we don't use fossil fuels at all.
Yeah, I think it's going to happen more quickly than most people think. So that's been the history of solar, as things have happened, like much quicker than anyone forecast. Like even 5 years ago, this thought that solar might provide most of our electricity by 2040 or 2050 was just being regarded as outlandish.
Yes.
But now it's accepted by almost everyone. So in Australia, we're adopting solar quite quickly, solar and wind, and battery storage. The three components needed. And South Australia, one of the states of Australia, is looking at being 100% renewable by, I think it's 2030. So
like 2030?
Yeah, so getting there quite quickly. And, Australia has largely been dependent upon coal for electricity production.
Yes.
I guess 10 years ago, it was probably 90% of our electricity came from coal, but now it's down to, 40% from black coal. And that percentage is going to drop very quickly because the Australian electricity market is sort of based on a free market system, and the solar is cheaper, and it's just making it difficult for the coal plants to compete. So they're disappearing a lot more quickly than anyone projected. Like even 5 years ago, the rate of disappearance of the coal plant is much more quickly, which is causing some alarm because people are confident that this new combination of wind, solar, and battery storage can provide power reliably, like fossil fuels are reputed to have done. Although, of course, there's been blackouts and so on caused by unavailability of fossil fuel plants, in the history of electricity supply.
Yes. So, our audience are the ones who would be deciding on their career in times to come, or who are already in their colleges and like you might move from physics to engineering physics to something like a solar to a photovoltaic. What is it that you would tell them about the kind of interesting things that can happen in the 20, 30 years of their working life coming forward? What could be exciting areas that could make an impact?
Yeah. Well, we're in a year of energy transformation, so it's going to be completed over that period. So there's going to be all kinds of changes. So we're starting to see the beginning of it now with the uptake of solar and wind that's occurring, and electric vehicles starting to change transport and so on. And if solar does become insanely cheap, we have all kinds of new applications and possibilities that are opened up by that. And
what kind of applications you would think?
Oh, my imagination probably isn't strong enough to comprehensively cover it. But in all kinds of consumer products and so on is sort of one type of application. But there's like everything can be energized, I guess. So it's the whole system that can be energized. So we probably will be able to, there'll be things like wearable solar, that there's already some pioneering products in that area, but the difference will be that they'll be incredibly cheap, I guess, if you go down the track. So you won't have to plug things into, and they're like your mobile phones, you'll just be able to wear them and put them in your pocket. They'll be recharging as you walk around. So I think this energy transformation, but I guess the other aspect of it, the energy transformation sort of permeates all branches of engineering and society, so that there's all kinds of jobs that get developed in an area of transformation like that. And so in solar, it's not only the technology of developing the cells and so on that I've been mainly involved with, but there's in the applications area. So the grid networks are designed for power being pumped from a big generator to the user, but now we have to have a grid network that's much more interactive and so on. So there's all kinds of opportunities for new products and engineering services and so on as a result of that. So that's just the areas that I'm most familiar with, but there's all kinds of novel applications for the solar, in the small systems that can, the good thing about solar, it can be deployed in really large systems or really small systems. Its modularity is one of its key strengths. So, all kinds of small applications for the solar that people will dream up through their creativity.
Yeah. So, I read somewhere that at one point in time, there was a thought that, you can use the desert of Africa for miles and miles of solar cells, and you have one high voltage direct current line going into Europe to supply all the energy needs of Europe. And then at the other end of the spectrum, you find this small grids where the electricity is made and used in small independent pockets of this. So what do you see is likely to pan out?
Yeah, so I think we'll see the whole range of applications. So in Australia, the main use of solar is on residential rooftops. So just small systems that supply the power to the electricity network, the different opposite direction from what it normally flows.
Yes.
From the house to the other users. In Africa, I think because they haven't invested to the same extent in distribution networks, it'll probably be small systems, maybe at a town or village level, that the format that the solar will take. But for places like Europe that have a well-developed distribution network already, piping electricity from a concentrated source like the Sahara, and it's certainly technically feasible to supply the electricity from there. So you might have these massive fields of solar that can pump the electricity to Europe. And our office in some parts of Europe is blessed with as much solar as India or wind, or India or Australia. But although the wind is good in the northern parts of Europe where the solar is weak.
Yes.
So I think all kinds of applications, from personal use or personal at the personal level, small systems for that. Like a digital watch, even level is probably smallest I could think of. To household, and then to village, and then country or European-wide solar deployment.
Yes.
So the whole range, I think, we'll see solar deployed, or we already are seeing it deployed at that whole range of applications.
Well, this is very exciting. So, what we have heard is a story of 50-year-long career.
Yes, it's 50 years this year, so it is
a long career in such a fulfilling way, And I don't think that there are many people who could see the result of their work, and it's such a wide-ranging impact on the world, as you have seen. And I call this as a beacon of hope and a blessing for the humanity. And I think that is what good technology, good science, good engineering makes possible. And we do look forward to seeing more of you get into areas as impactful as Dr. Green has done. I am certain you will enjoy this interview, and we will keep on coming to you with such extraordinary personalities as Dr. Green. Thank you so much, Dr. Green, for being with us.
Thank you, Ravi. It's been a pleasure talking to you.
My pleasure.